as being a major contributor to fault strength. And that's great, right? That led us to like modern rate and state friction theory, earthquake cycle models, all of the things that we have today. But one thing that I have started to focus on in my group recently is that fault strength is not only controlled by the friction coefficient, it's also controlled by the normal stress, which I think has received like plenty of attention or a lot of attention. But something that hasn't received as much attention, hopefully it's not controversial to say that, but something I think hasn't received as much attention is the C, so the cohesion term. And if anything, you know, if you walk away from this talk with anything today, I would like you to walk away with the idea that maybe cohesion, there's some places where cohesion can be important, and it may be more important than we think it is. Okay, so I'm going to tell you a story, and that story is the story of slow slip. And so I don't know if you know this, but slow slip was an accidental discovery. Basically, if you are a seismologist and an earthquake happens somewhere in the world, you can go and you can pull seismograms up and you can take a look at them. And they look kind of, you know, and they look different in different circumstances, but there are certain features of waveforms that we look for. And so traditional earthquakes have impulsive, easily identifiable, like P and S waves, like you can see on the diagram on the right. They often occur at many stations across a network. The timing of the arrivals is indicative of the source location. And then, you know, there's other things too, like the amplitude is largest on the station that's closest to the earthquake, et cetera. And, you know, this is sort of what people were used to looking at that time. But the seismic signature of slow earthquakes is actually really subtle and was discovered accidentally. So Kazushige Obara was a seismic network analyst in Japan. And one of the ways that they assess network health is they take stations, they organize them as a function of latitude, and they take and they filter them in different frequency bands, and they sort of look at how things look to see how healthy the network is. And while he was doing this, one of the things that he noticed were these, what he called small amplitude tremors that lasted from a few minutes to a few days. They're most apparent in the 1 to 10 hertz frequency band. And they're difficult to locate because you can see this looks very different than the example of the earthquake that I showed you before, but there's not really like these impulsive P and S wave arrivals, but you can apply some crude methods that put them at around 35 to 45 kilometers depth, which was the depth of the subduction interface. And at the time, Obara-san, he put forth like a lot of different explanations for these things, but I think it's important to note that these weren't yet linked to slow earthquakes. And so meanwhile, in Cascadia, there was another group, Megan Miller et al., looking at slow slip and GPS. So GPS, as you all probably know, measures the deformation of the Earth's surface. And in Cascadia, basically this diagram on the right shows the baseline length, which is just the distance between every point on the map and the station in the top right, which is DRAO. And so what you can see is that stations that are near the coast, like NIA and PABH, they have sort of an interseismic trend that's very steep because they're close to the active margin, so that it's being compressed and the baseline length is decreasing as a function of time. And that trend is there in all of the GPS records. But one of the things that you can see in certain spots is that the GPS record will go down and then it sort of pops back up, goes down, pops back up. And then as you start to get more and more GNSS stations, what you can see is that there are these sort of transient reversals that take place over the course of a couple of weeks. And so basically they linked this to sort of these periodic slow earthquakes in Cascadia that manifest as these transient short duration reversals. And we know that they're real because they manifest across multiple different stations in the network. So I got an updated diagram from Tim Melbourne, and this is like a very complete GNSS record from Cascadia for over 20 years. And anyway, you can see that there's all sorts of slow slip events, so that's fun to look at. Anyway, finally, Rogers and Dragert linked tremor and slow slip. They basically put both the GNSS data and the recorded number of tremors on the same diagram. And what you can see is that whenever we have these transient reversal periods where the east displacement decreases, you have a large spike in the number of tremor, and that linked tremor and slow slip for the first time. And so this is Aaron Weck's tremor catalog. And, so we took those ideas. Aaron Weck and the Pacific Northwest Seismic Network created this sort of long duration tremor catalog. It's one of the best in the world. And what you can see here is there's basically on the left-hand side, there's a map that shows tremor epicenters as that are occurring in certain time windows. On the right, you have time versus latitude. And you can see that, a slow slip event will start. It's delineated by tremor. They migrate all sorts of different ways up and down the margin. They're more frequent in certain places like Southern Cascadia near the Mendocino Triple Junction than others. But this is like a really rich catalog and a really rich data set. Anyway, so I guess all of that happened back in kind of the early 2000s, early to mid 2000s. And, I think it's kind of worth like reflecting that, we're more than 20 years into the field of slow slip. And there have been, tons of papers, thousands of papers published on slow slip. But if I had to sort of distill kind of the communal knowledge down into a few bullet points, this is what they would be. So we now know that there are places where slow slip happens and places where slow slip does not happen. We know that it occurs. It's not linked to a single thermal or petrological environment. That's what's shown on the diagram in the right. You see also the different subduction zones hosting slow slip are shown in the colors. And you have temperature and pressure on the X and Y axis respectively. And you can see that places where slow slip occur, i.e. where there's color on the diagram, they happen over a variety of different metamorphic facies. So there's a variety of different thermal and petrologic conditions involved. Another thing that's come to light, or I think is pretty well accepted, is that slow slip appears closely connected to high pore fluid pressures. There's a few different lines of evidence that suggest that they happen in the presence of near lithostatic pore fluid pressure. We also know that at times slow slip events can precede large earthquakes, but it's definitely not universal, though it's certainly a hot topic. And then I guess I would argue, maybe this is controversial, and that's fine. But I guess I would argue that like we've learned a lot, but it feels a little bit to me like things have kind of slowed down a little bit. Like there hasn't just been like the steady advance that there was early in the field, which is probably normal for new areas of study. So thinking about the possible mechanisms, a number of different things have been proposed in the literature. But I would say that after 20 years, there's still no sort of consensus on the processes that cause slow slip events. Like this is still not really agreed upon. There have been suggestions. This is a not comprehensive list of the different suggestions that are out there. So you have things like tuned length scales. You have rheologies that evolve from being velocity weakening at low slip speeds to velocity strengthening at higher slip speeds. You have things like dilatancy, where as you shear, you dilate the fault zone, that drops the pore fluid pressure and quenches slip. You also have people implicating various flavors of heterogeneity, but what specifically sort of depends on the particular paper. And, if anything, I just think like this is a field, I consider this to be one of the great unsolved questions in geophysics, is what causes slow slip events. And I would say like this is just a field that needs new hypotheses and new ideas. And, if one of the most significant discoveries in solid earth geoscience isn't worth studying, what is? So this is my rallying cry, my appeal to the community to do more slow slip work. Okay, so we're going to move into Cascadia here and low frequency earthquakes. So low frequency earthquakes are a type of earthquake, and we think essentially that the tremor signature that I showed you before, the one that Obara-san found that sort of led to the discovery of slow earthquakes, I think it's pretty common knowledge that this we think is mostly or entirely a superposition of what we call low frequency earthquakes. So low frequency earthquakes are, they're similar to high frequency typical earthquakes. It's just that if you were to compare a typical earthquake of a certain magnitude and a low frequency earthquake of that same magnitude, the low frequency earthquake would be depleted in high frequencies relative to the traditional earthquake of the same size. It's sort of finding LFEs is a little bit more work. Finding and compiling LFEs is a little bit more work. than just studying like sort of the raw tremor. But there's a lot of advantages to doing that extra little bit of work. One of them is that working with LFEs facilitates, I had talked before about how there's, the tremor onsets are emergent, there's no clear PNS wave. If we go to the extra effort of finding the LFEs, you have clear PNS waves, which allows you to sort of locate them precisely and get an estimate of the source location and then the properties in the source region. And they're also thought, these LFEs, they're pretty small overall. The magnitudes don't really get up much above magnitude 2. And they're generally thought, we can see geodetically that there's a lot of slip happening down there. Like in Cascadia, sometimes slow earthquakes get up into the high magnitude 6s. But these little patches, these little asperities that are radiating LFEs are very small, and they're just basically thought to be kind of passive indicators of the surrounding slip. This is a little bit of a debate as to what they are, but this is sort of the viewpoint that I've adopted throughout the rest of the talk. Okay, so what we're going to do is, this is Michael Bostock's low frequency earthquake catalog in southern Vancouver Island. It's just a map. Each colored dot on the map is a hypocenter or is an epicenter of a low frequency earthquake. They're color coded by their depth. And in the next couple diagrams, what I'm going to do is show you space-time plots. And I just want to point out the space axis goes from, let me see if I can find my cursor here. Oh, I cannot find my cursor. Okay, it went away. Anyway, the space-time axis just goes from -40 in the bottom right corner in the southeast to +40 in the top left corner to the northwest. Okay, so we're just going to be plotting LFEs as a function of space measured along this line, which is parallel to the local strike, and then time. Okay, so if we take a look at a slow slip event that happened back in 2009, what you can see is this sort of broad picture of broadly the slow slip event is migrating from the northwest to the southeast. So you can see that because the hypocenter dots go from +40 down to sort of -40 over the approximately week-long window that's shown here. And another thing that, is informative is to sort of take and start looking at LFEs as a function of time at a fixed position in space. So what we're going to do, the main front here, going back to what I just said. The overall slow slip event is migrating sort of south along the margin at around 5 kilometers a day. But what we're going to do is take a look at this LFE 141. It's just a particular low frequency earthquake family that happens at around 8 kilometers along strike as a function of time. And so what you can see is, so we have these LFE families. So there's date and magnitude, date on the x-axis and magnitude on the y-axis here. And what we think is that sort of LFEs, repeats of LFEs sort of reflect slip on the same sort of region of the fault. It doesn't have to be exactly the same spot like it is in sort of shallower repeating earthquakes where the waveform similarity is 99%. But in general, you can think of LFEs as sort of reflecting an LFE family as reflecting slip on the same sort of region of fault. And then during SSEs, slip as reflected by LFEs is really unsteady. And so what you can see in the diagram on the bottom right is that the moment release overall is really unsteady. You have like big bursts of LFEs during the main front as the main front is passing through. So you can see those on like September 9th or September 10th and September 11th. And then as like time progresses, the main front passes, you still have sort of moment release, sort of LFE bursts that are happening, but there seems to be sort of a pause and then a burst and then a pause and then a burst and then a pause and then a burst. And so all I want you to get out of this slide is just that the occurrence is pretty unsteady. Similarly, like, we just took a look at an LFE in space as a function of time, but let's take a look now at a fixed kind of position in time, but in space, but variations in space instead. And so one of the things that we see when we do that are these things called what I call secondary slip fronts. And these are LFE and tremor sort of migrations, and there's several different pieces of literature on them, but in general, what happens is that they reverse, meaning the main front is moving from north to south, and after the main front passes, like in its wake, within a few kilometers of it, somewhere between 1 and 10, sometimes you nucleate these secondary fronts and they propagate backwards through the portion of the fault that just slipped in the previous day or two during the main front. So these things move through the region that's already slipped, and they do so fast. So they're going around 10 to 40 times faster than the forward propagation. They can move like 10 to 50 kilometers over a few hours, and they generally begin kind of right in the wake of the main front as they propagate backwards. Okay, yeah, sorry, I already said those things. Okay, and so one of the things that we've recognized is these secondary fronts are kind of like a ubiquitous feature of slow slip and Cascadia. So you can see anytime you see sort of a vertical streak of hypocenters on this diagram, those are secondary fronts. And if you take a look at the weak gray line or the weak gray plot at the top of the diagram, one of the things that you can see is that if you take a look at the LFE moment release as a function of time, these these secondary slip fronts are sort of dominating it. They have the LFEs and the secondary slip fronts, because they occur in bursts, there's like a high moment rate associated with that. The other thing is the LFEs that are happening as part of the secondary fronts tend to be higher moment or higher magnitude than the ones that happen earlier on in the slow slip event. And so I just have been kind of obsessed with these. I think they're really interesting. And so one challenge with studying these is you can take a look at tremor and LFE space-time migration patterns, and that's great. But if you want to get at more accurate estimates of the total amount of slip that's happening in these things, it's a little bit challenging. And the reason it's challenging is just because they only last a few hours. And for those of you that work with GNSS data, you know that the shorter the time scale you go to with GNSS data, the larger the uncertainties. And so it just becomes really challenging to see these smaller magnitude secondary slip fronts in the GNSS data alone. But one person, Jessica Hawthorne, did do sort of a deep dive, a pretty comprehensive deep dive into strain data, so strain records. And the point of the study that she wrote was just trying to compare and better quantify some of the properties of these RTRs, or she calls them RTRs, rapid tremor reversals, but they're the same as the secondary slip fronts it's the same term. So Jessica did sort of a comprehensive analysis of the strain data. She did a lot of identification. You can see sort of transient drops in the strain at times. In the diagrams on the right, you can see sort of transient drops in strain at times when these secondary slip fronts are happening. She did a really good job of quantifying the uncertainties. And one of the things you can do is come out with sort of a comparison of the RTRs to the total slow slip front. And so RTRs, like the moments, can be up to magnitude 5.1, whereas the moment release in like a day of slow slip event is around magnitude 5.6. You can estimate like the total amount of slip, and that seems to be like around 16%. You can estimate the slip rates, that seems to be a lot higher in the rapid tremor reversals. And one of the things that caught me with this study is that she could estimate sort of the stress drop associated with both the SSE, the main front, and then the rapid tremor reversals. And when she does that, one of the things that she gets is that the stress drop in these RTRs is around 47% of the stress drop in the sort of SSE, the main front of the SSE. And I just thought this was weird. And the reason I think it's weird is that that's a pretty large fraction of stress to be dropping relative to the main front, given that these secondary slip fronts only happen in like a few hours to a day after the main front passes. So we'll come back to that in just a second. But Jessica and Jessica Hawthorne also has done a lot of work sort of trying to model the secondary slip fronts. And then there's also been follow-up work on this in Alan Rubin's group. And basically, one of the things you come away with after reading those papers is that frictional models of SSEs can't really reproduce realistic fronts. And I'll quote from their paper, "The modeled fronts do not seem to be a reasonable representation of the fronts inferred from tremor observations. They require implausibly large stress drops to reach the observed propagation rates, and unlike some of the fronts observed in tremor, they do not repeatedly rupture a single region." Okay, so just thinking about this a little bit more, you can ask yourself like the very basic question, so when do faults slip? And at the most basic level from your Earth Science 101 class, This is a slide from my 101 class. Fault slip when the stress exceeds the fault strength. And so taking and just applying that simple logic and asking the question, well, what processes could drive these secondary fronts? You can ask the question, well, you just had the main front pass and you relieved stress during that. You've had like another day or a few hours to accrue stress. And so you ask the question, well, what stresses the fault? So the fault just slipped. How does it regain stress? Well, one way that is maybe surprising is the tides. And I know that seems crazy, but it turns out that low frequency earthquakes and tremor are really sensitive to tidal stresses as the slow slip event is going on. You can take a look, and the main front itself, the sensitivity is not very strong. But these secondary slip fronts are essentially almost 100% triggered by the tides. Okay, so the tides they reload the fault. They supply something like around 2 kPa of shear stress to the fault, and something about that process tends to trigger the secondary fronts. But the other thing is that the secondary fronts, like the stress drop, is more than just 2 kPa. So you need not only the tides, but you need another source of stress. And so there has to be something else going on. So, pore pressure waves or something like additional stress transfer from the main front, which is sort of still propagating to the south in this example that I'm using. But even if it's propagating to the south, if this part of the fault is sort of stuck, you're continuing to transfer stress, and it could drive it up over the failure threshold. So what recesses the fault? It's the tides and something else. And then, so the other question though, right, is to have a stress drop, it's not enough to just apply stress to the fault. Like if the fault just slipped, it should be really weak. If you apply stress to a really weak fault, you would think it would maybe just creep and relax those stresses away. But instead we see these, pretty significant secondary slip fronts that are accommodating a good chunk of the moment budget of slow slip events. And so if you apply stress to a fault with no strength, it'll just creep. In order to make rupture fronts, you need to not only reload the fault, but you also need to re-strengthen it. And so you start to think about, well, what processes could cause rapid re-strengthening? And I went on sabbatical to Syros with Whitney Bear, and this is a picture from that trip. And one of the things that you can see all over the place is veins, so quartz-filled veins. And so, this is like a seismologist's take, but I started thinking about processes like cementation. So in these deep slow slip environments, we think that there's significant fluid-assisted mineralogical and chemical processes that occur within fault zones and can strongly influence their properties. Cementation, there's a lot of nuance to the different terms that we use to describe processes, but here I'm just saying that cementation involves precipitation of minerals or other solid phases from fluids into the sort of interstitial space of a rock mass. The interstitial space is generated by deformation processes such as SSEs. And so the idea is that this cementation causes healing or increases in fault strength. And this could potentially be an important process for the dynamics of slow slip events, and in particular explaining these secondary slip fronts. And so we went and did kind of a deep dive into not a deep dive, we went and did a survey of the literature. And, with rate and state friction, you have your slide hold slide test, you have your velocity stepping test, you can get your A and B, and you're sort of off to the races. I know it's a lot more complicated than that, but at least there is like sort of an experimental paradigm that allows you to determine A and B. My reading of the literature, and Chris, I know you're working on this and I'd love to talk more about this, but like I came away from the literature, the deep dive of the literature on cementation of the lab, I came away with the idea that there's essentially like no experimental paradigm for how to measure cementation. People do all sorts of different things, like look at, they shock quartz to crack it, and then they heat it back up and they measure like the length of the crack from the nearest like inclusion bubble, and all sorts of different things. So there's no paradigm, but what you do come away with is, look, there's a lot of evidence that things heal pretty fast. So you have things like 4 hours at 600 degrees C and a water pressure of 200 MPa. You have 6 hours at 927 degrees C, which is a little hot for our purposes. But in general, what I came away with was just the idea that, hey, maybe it's like not unrealistic that on a few hour time scale, you actually may be able to do to have some strength recovery from cementation processes. And then like there's some other reasons why this is attractive. And they are, basically pressure temperature conditions in the slow slip region favor rapid cementation. So the mineral reactions that you would need to happen, right? They're usually a function of the temperature and the pressure. So the hotter the temperature, the faster the chemical reactions that drive cementation can take place. We see cementation all over the place in the rock record. Like if you go to Syros and other places that are thought to have been exhumed from these environs, you see a lot of evidence of this. Effective stress in SSE environs is thought to be very low. And if we go back to our fault strength equation, right, we have the strength equals cohesion plus friction multiplied by effective stress. If the effective stress is low or near zero, then that sort of leaves you with cohesion as being a potential contributor or one of the only contributors to fault strength. And then finally, like there's almost no sensitivity of LFEs to, like, we talked about the shear stresses, but tidal normal stresses essentially like make no difference. And so you're looking for some normal stress independent mechanism that could potentially contribute to fault strength, and cementation kind of checks that box. There's some other problems that it fixes as well. So faults are typically rate strengthening at elevated temperatures and pressures. In Cascadia, we're at 1 GPa and 500 C. And you would think generally you'd be in a velocity strengthening regime there and not really able to host unstable slip. Another thing is like having really low effective stress makes it challenging to explain LFEs to get small scale radiative. If you have really low effective stress, it should be a challenge to get small scale radiative failure. Conditions employed to regulate slip speed and models of large scale SSEs sort of prohibit that. And then cohesion provides like additional fault strength. And if you recall that quote from Jessica Hawthorne that they needed some additional mechanism for strength recovery, cohesion could in addition to friction, cohesion could potentially provide that. So that additional source of stress drop might allow these secondary fronts that they model to be more reminiscent of the ones that we actually observe. Okay, so I am married to a petrologist, and I had to nag him for about a year to help me out with this, but he finally gave up. And anyway, I asked him to help me out by doing some fault healing experiments. And so what we did is he works typically, we have piston cylinders, right? And so these are experimental apparatuses that can take small rock samples up to the conditions of SSEs in Cascadia. So things like 1 GPa and 500 C. And what you can do is ask the question like how strong, right? Like, so what happens through time? And then how strong is the resulting cement? And sort of just the experimental motivation for this was like you have a deep shear zone, you have more intact wall rock, and then sort of less intact near sort of where you would ultimately host the slow slip event. And then you have sort of a stress buildup pre-SSE, and you can think that things are sort of relatively compacted, and then during slip you have faulting, and that faulting sort of maybe cracks or breaks the surrounding rock, and you have dilation and enhanced permeability. And then the question is sort of what's happening in that post-SSE time period. So right after you've fragmented all this rock, very early in the healing process. And if you recall back to the secondary slip fronts, right, we're talking about the fault just having slipped in the main front, and then in the few hours to the day after where you start to have these secondary slip fronts, the question we're asking is what's going on there? So this is the experimental design. He took sort of coarse-grained ground crystalline quartz at 125 to 180 microns, subduction fluid, which is essentially seawater without magnesium. He loaded it into a silver capsule. The silver capsules are really small. I forgot to bring one, but they're itty bitty. They're around 3 millimeters tall and a little over 1 millimeter wide. So this is a pretty small sample. And then we squeeze and we heat it for some time, and we look at what happens. And we not only look at what happens, but what we're doing here is petrologic time series experiments. So each sample is unique. and you take it up to the right pressure and temperature. You hold it there for, let's say, 1 hour. You bring it back down, and then you look at what happened. You take a different sample up to pressure and temperature. You leave it there for 6 hours. You take a look and see what happened, and so on and so forth. So this is just an example, like an SEM image of the starting material, and there's all sorts of stuff that you can see here, but among it, you see conchoidal fracture. That's where you've sort of broken this like silica. You have things like angular edges, you have electrostatically attracted quartz, but this is just effectively an SEM image of powdered quartz, and so this is the starting material. So the next image is going to be what we see after about 6 hours, and you can see that the character after 6 hours changes pretty dramatically. You can see things like growth of small sort of new grains. You can see things like intergrown crystals. You see things like rounded edges, and none of these features was sort of present in the original starting material. And so this points to sort of dissolution and precipitation processes that are going on under the pressure and temperature conditions while we hold the samples. At 12 hours, it just looks like kind of a more evolved version of the 6-hour material. So you see things like protofacets. So that suggests that there's like new mineral formation. You have more interlocked crystals. And then after, in the 24 hours, you can start to see things like fluid inclusions. And if you zoom into certain areas, you see all sorts of different facets and things. So just generally, it looks like even on, time scales of less than a day, you can get sort of significant reworking and significant dissolution precipitation happening in these samples. And so if you remember from before, like ideally what you do, right, is you have these samples that you've cooked for some amount of time, and they come out of the piston cylinder. And ideally what you do is just like pop them in a triax, right, and do deformation experiments. But it ends up being a lot more complicated than that because the samples are really, really small, 1 millimeter by 3 millimeter. There's no triax, I don't think, in the world that can go to that small sample size. We're trying to modify the piston cylinders to actually be able to do big samples. That's ongoing work. But yeah, so there's some experimental challenges. Get the silver jacket is another problem. All I hear about is problems. But anyway, the bottom line is it seems like things could potentially heal really fast, like on tidal timescales fast. It's hard to measure how cohesed something is. And you can't really like usefully interpret the implications for fault strength without a way to measure cohesive strength. Like we can look at the samples and we can poke them and we can say, hey, this is like really welded together and it seems like it's, it's completely cohesed, but we need something a little bit more quantitative. And so what we ended up doing were wave speed measurements. And so with the wave speed measurements, you just have transducers on both sides of the sample. And you just look at basically the speed of a P wave, the relative speed of P waves as they propagate through the different samples. And just the idea is that if you're, initially you're starting with like sort of pulverized quartz and there's not any cohesion at the contacts. And so the wave speed probably just measures is some function of like the jacket that's around the sample. But then as you cook these samples and the contacts get more and more competent, right, you're increasing the Young's modulus, and that helps with your P wave propagation. So you see increases in wave speed that we think are a function of how cohesive the sample is. And so just as an example of that, on the left-hand side here, this is the experiment duration as a function of time. And then on the y-axis in panel A is the percent change in wave speed. And what you can see is that there is an increase in the wave speed, a significant increase in the wave speed as a function of the experiment duration, as we would expect. You can do some a little bit of some speculative stuff and take some relationships that are in the published literature that allow you to convert those changes in wave speed to estimates of changes in cohesion. Okay, so overall, this gives some confidence that cohesion is on the cohesive strength recovery is on the order of megapascals. But I wouldn't put more confidence, I wouldn't overinterpret it. I just think generally that it increases is a good sign. And then also that we're in the ballpark of 3 to 4 MPa. The other thing that we get asked a lot is like, what is the specific healing mechanism. So what is causing the dissolution and precipitation that we see in the capsules? This is a little bit of a complicated question. We know it's not equilibrium solubility. At first, I sort of favored pressure solution, but the idea when you start compressing these things is that the lithostatic stress or the pore fluid pressure should become lithostatic pretty fast as you compress the capsule. And if you have near lithostatic pore fluid pressure, it shuts off pressure solution. So I'm not sure that that's a viable mechanism either. But there's some other kind of neat work about what the micro, like physical processes that drive dissolution precipitation are. And this is some work from Beeler and Hickman, where they did a studies of experiments that just involved like sort of a lens that they submerged in 500 degrees C water. And they just observe optically sort of growth of essentially contact overgrowths in those experiments that are driven by what they call like gradients in surface energy. So just sort of purely in a geometric way, you can get dissolution and precipitation just from gradients in surface energy alone. But the dissolution precipitation mechanisms and their rates is, I think, like a really outstanding question in geosciences generally, and I'm happy to talk more about that at the end of this. Anyway, summary of experiments, I would say things heal pretty fast on, less than day-long timescales. Cohesive strength is on the order of a few MPa, and the micromechanisms are probably gradients in surface energy, but it could also have some contribution from pressure solution. But it's not by bulk chemical supersaturation. That's one thing that we don't think is happening. Okay, so we've shown some observational evidence potentially for cementation and cohesion being important. We've shown some lab experiments that suggest that it can happen on the timescales and quantified the overall strength. The very last thing that we're starting to do is work on basically incorporating realistic timescales and amplitudes of cementation into earthquake cycle models. And so that's ongoing work in my group by graduate student Darshika and a postdoc that's on his way. But basically, we did a little bit of preliminary work on this, and I wanted to just point out, so this follows some stuff that Nick Beeler laid out in a really great paper from 2022. And as he dives into the modeling section, I'm going to quote Nick, but he says the calculations that follow should be considered both qualitative and speculative. So the first step in developing sort of any numerical models of fault friction or slider block models, these incorporate sort of very basic physics, but don't include sort of, elasticity in the bulk. So they don't include like stress transfer between elements, but we're just trying to understand, to first order, can cohesion produce stick-slip behavior? And so the way that we model this is just sort of the normal way that you would set up a slider block model with rate and state friction, except instead of just having the fault strength equal mu times the effective normal stress, we add a cohesion term, and that cohesion term is time dependent. And so here we have cohesion equals tau sub c. Tau sub c is a material property that is essentially that strength that we measured from the experiments. And we say that the AFT, which is the area of contact at a time t minus the initial area of contact. And this is just meant to say like, okay, like let's say initially you have two surfaces together, right? And you have the frictional contact area, that's in the black. And then if you sit there and you hold it and you let mineralization happen, or like those contact overgrowths, let it, like I showed you in Nick's experiments, at time 2, the contact area will have increased a little bit. And that increase in contact area is due to like cementation. And so this cohesion term just captures that time-dependent cementation. The way that we constrain this is we use the rates. The way that we kind of constrain the rate is we use the contact overgrowth experiments that Nick did in 2015 and then represented in 2022. But he has estimates of how the fractional contact area evolves as a function of time. And so that was the sort of time dependence that we put in here, since it wasn't really constrained by or wasn't fully constrained by the experiments themselves. And then the rest is just the usual stuff. You have a driving stress, a radiating stress, a resisting stress. It's just essentially the same setup, except We added cohesion, and then we consider purely rate strengthening friction. So there's no B term here. It's just purely rate strengthening. And lo and behold, if you ask the question, can cohesion produce stick slip behavior? The answer is yes. Yes, it can. We kind of knew this before we did any modeling, but it's nice to, see it in a simple just block slider model. And like I said, kind of the next step with this is to start looking at this, doing more complicated earthquake cycle modeling that includes cohesion and trying to say, well, can we, explain the secondary fronts and the influence of the tides and other things. So overall, yeah, my conclusions are just cohesion could play a big role in generating secondary, not a big role. Cohesion could play a role in generating secondary slip fronts that are commonly observed in SSEs. We have rapid healing. We think rapid cohesive healing could potentially occur at pressure temperature conditions of Cascadia SSEs. Mineralizations from our experiments, we think have strengths of 1 to 4 MPa. And then really primitive numerical models indicate that cohesion plus rate strengthening friction can produce sort of stick slip-like behavior. And then just overall, like slow slip, I think is really worth studying. And also, I think there's kind of a value in reevaluating the role of cohesion generally, because I think there's places not only in slow slip environments, but any place in the earth where you think the effective stress may be close to zero is a place where cohesion could potentially play a role. So that's it. That's all I have. Thanks for
That's
listening.
fabulous. Thank you very much, Amanda. That was a fabulous talk. I will invite people to unmute and join me in thanking you for a great talk. And yeah, and then, okay, we can ask people to use the raise hand feature at the bottom of your screen. I'm sure you know, but it looks like this. And yeah, it's a great way to put ourselves in some order to begin to have a discussion. Lots of people are still finding cool things to send across the screen. Awesome. Yeah. And yeah, so we give Amanda just a minute to catch her breath, but
I'm going to take a sip of water here.
yes, thank you. Yeah, so okay, while you all are still thinking for just a minute, I'd like to start one question, maybe just a couple slides back. The little modeling you were doing, that velocity, was that particle velocity or was that some kind of rupture velocity? Because this velocity right here, it reaches kilometer per second, and that seems like it must be a fault slip velocity, right?
Yes, I mean this is it's just a slider
Yeah,
block. So it's just
right,
the relative velocity between
right,
the
okay.
interface
Yeah,
across the interface. Yeah.
it's
So
a even the slider block models typically for rate and state friction give, values that are closer. I mean, and usually with rate and state friction slider block model, you need some kind of radiation damping. You need something to kill the energy to stop the velocity to go to infinity. And you have
well,
some,
we did. Yeah, that's a great question. Sorry, I haven't looked at this in a while. We did actually put radiation damping
okay,
in here.
yeah, okay,
And so we didn't, I guess like what I should say is this is not like something that I published or anything. It was really just sort of a thought experiment to see
yeah,
like, can you get it? I didn't put any effort necessarily into like trying to tune to see if like, slip velocities of, to try to see if I could match like slip velocities of LFEs or things like that.
okay.
So.
Um, I'm gonna make an obvious announcement if you were paying attention. Okay, first of all, I'm sorry I forgot to start the recording at the beginning, and I'll deal with that. But when this gets put online, and second is that I'm now stopping the recording.